Hello viewers, we are now taking you through the story for A-Level Physics Paper 1. And this video I'm going to go through the topic of atomic physics and shall mainly concentrate on the part of electron dynamics. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from those topics. And the second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So you already finished part 1, part 2, part 3, part 4, part 5, and now we are on part 6, which is atomic physics. So atomic physics, because of its wideness, it has been broken down into 2 parts. There's a part which will concentrate on electron dynamics, and that's what we are going to look at today. Then the second part will concentrate on Millikan's oil drop experiment. So here we are interested in calculations on this YouTube channel, but complete notes, worked examples, and try questions of all the parts of physics paper 1 are available in this book, Mastering A-Level Physics Paper 1. And if you need a copy, you can contact the author on any of these 2 contacts. So the questions we are going to look at are the very questions in the worked examples of this book. And a complete set of physics has 3 books. The first book is Physics Paper 1 we have looked at, then Physics Paper 2 and the Topical Question Bank. Then if you also do Principal Math, there are 3 books, Math Paper 1, Math Paper 2 and the Topical Question Bank. For Subsidiary Math, it is only 1 book. And the rest are for physics. There is O-Level Physics and O-Level Math. So now shall start our topic of atomic physics, or what we call electron dynamics. So if cathode rays are assumed to consist of particles, in brackets electrons, to which the laws of mechanics apply, we can obtain information about their speed and specific charge. So atomic physics is mainly concentrates on the speed of an electron and also specific charge of an electron. Now specific charge is simply a ratio of charge to mass. So if you know the charge and you divide it with mass, then you will have got the specific charge. So these are the 2 main areas we shall concentrate on under atomic physics. And also the third part is this behavior in electric field. So its behavior in the electric field deals with deflection. Is the path taken circular, elliptical, straight, like that? So that's what they mean by behavior in electric and magnetic field. So that's what we shall look at. How does it behave when in an electric field, and how does it behave when in a magnetic field, and how does it behave when in a crossed electric and magnetic field? So all those parts will be looked at in this video. So we shall start with speed. So speed of electrons. So we shall consider an electron of charge E, that is the electronic charge, and mass ME, that is the mass of the electron, which is emitted from a hot cathode. Remember, we have already seen that when a cathode is heated, thermionic emission occurs, and thermionic emission means emitting of electrons when the surface is heated. So when the cathode is heated, electrons will be emitted, and these electrons which are emitted will be accelerated by an electric field towards the anode. So there will be an electric field between the cathode and the anode. That's what enables the electrons to be accelerated, and that field is produced by what we call the accelerating PD. So I think you remember when we looked at X-rays, you remember that accelerating PD between the anode and the cathode, V.A.K. So we are going to also use it here in our part of speed of electrons and other parts. So this electron experiences a force due to the field and work is done on it. So we shall illustrate later, but let's first look at this. So the system, in brackets the field and the electron, loses electrical potential energy and the electrons gain kinetic energy. So what does that mean? It means that if V.A.K. is the PD between the anode and the cathode responsible for the field, and that the electron starts from cathode with 0 speed and moves in a vacuum. Vacuum means there is no air resistance, or air resistance is negligible, attaining a speed v as it reaches the anode. It implies that the kinetic energy gained will be equal to the electrical work done. So you're coming and say that electrical work done is equal to kinetic energy gained by the electron. So electrical work done is given by the formula charge times PD. So in this case, the PD is what we call the accelerating PD, which is V.A.K. And the charge, because it's an electron, it will be E, electronic charge, is equal to kinetic energy, which is a half mv squared. M will be the mass of the electron, and V will be the speed of the electron. And remember, you're interested in getting the speed. So when I make V the subject, I'll come up with this expression: 2e v divided by m. So before we go to the other parts, let's first look at the calculations which involve speed of an electron. So question 1 came from UNEB 2020, paper 1, question 10e, and it says an electron with energy 5 kilovolt moves in the direction of an electric field of intensity this. So this is the electric field intensity. What distance will the electron move before coming to rest? So first of all, we shall remember that electrical work done is equal to kinetic energy gained by the electron. Therefore, we shall come and substitute for electrical work done and the kinetic energy. Then here E is a constant, is known. So this constant of electronic charge will always be given in your examination, the first page. So E is a constant. Then V.A.K, it was given in the question, it is 5 kilovolt. So you change it to volt by multiplying by 10 to the power 3. Then the mass of an electron is also a constant. It will be given in your examination. Then V is what they want, the speed. So now we have only one unknown. Next is to simplify. When I simplify, this one gives me this and this gives me that. But there's a V squared here. So when I take this one this side, I'll come up with V squared being equal to, actually my aim is to make V the subject, so I put a square root of this divided by this to give you the value of V as that. But remember, the question wants the distance. What distance will the electron move before coming to rest? So the distance moved by the electron before it comes to rest. So first of all, you shall know that force is equal to mass times acceleration from Newton's second law. But also, this force is the electric force. Therefore, it will be given by electric field intensity times the charge, electronic charge, because it's an electron. And there is a negative, so you don't forget the negative there. Opposite directions. Now we are putting a negative because the force is acting in the opposite direction of the acceleration. So here come and substitute for a negative is there. Then electric field intensity, it was given the question. If we go here, this is the electric field intensity, so that is E. Then the mass is a constant. Now we have A. So still here in this line, it is only A which is the only unknown. Therefore, we can look forward to making it the subject. When I make it the subject, I'll come up with the whole of this, divide by this to give me that, with a negative because it is retarding. Okay, now that I've got acceleration, I can use the third equation of motion. V squared is equal to U squared plus 2AS. Final velocity is 0. That's what was given in the question. Initial is this one, which we got in the previous slide. Acceleration is that with this negative, and S is what we want. So when I make S the subject, I'll come up with this as the answer they wanted. Then question 2 came from UNEB 2006 per 1 question 9C, and it says electrodes are mounted at opposite ends of a low pressure discharge tube and a potential difference of 1.2 kilovolt applied between them. Assuming that the electrons are accelerated from rest, calculate the maximum speed which they could acquire. Specific electron charge is this. So like I told you, specific charge means the ratio of charge to mass. I think I can even get it from the unit, coulomb per kilogram, charge over mass. So first of all, you shall come as that electrical work done is equal to kinetic energy gained by the ions, then you substitute. Now here, it is not an electron, that's why you're using Q. So we shall use capital Q times V.A.K is equal to half mv squared. But the good thing, we know the specific charge, we know the value of Q over m. So what we are going to do, we shall rearrange and say that this m with this Q will be paired together to get the ratio which is here. Then take this to this side to give you 2 times V.A.K. Then because it is a square here, we shall put a square root. And in that we shall have made V the subject. Now next is to substitute. This was given V.A.K. Then this one is what we put here under the part of Q over m. So we shall ignore the negative so that we don't get an abnormal value here in the square root. So I'll just use the magnitude. Now when I use a calculator, the whole of this will give me this as the velocity or the maximum velocity. And that's what they wanted. So you have dealt now with the speed of an electron. What about deflection of an electron in a magnetic field, or behavior of an electron in a magnetic field? So here shall say that consider a stream of electrons entering normally means perpendicular, into a uniform means constant, uniform magnetic field, which is perpendicular. These words perpendicular are vital. Perpendicular perpendicular to and directed into the plane of the field as shown below. So directed into the plane is what helps you to get the direction of the force. So you first put the magnetic field, which is uniform, and into paper. So this is an inlet so that an electron can enter. So we shall put a negatively charged ion or an electron. So when it reaches here, I think you realize that it begins to curve. And when it reaches here, it goes in the straight line. We shall see why. So at point C, the force is downwards and the velocity is in this direction. Then at any other point, at point D, the direction of velocity is in this is here, but it is the same magnitude. I think we realize that here it is U and here it is also U, meaning magnitude is not changing. It is only direction which is changing. If you look at this force, magnitude is the same, but the direction is only the direction changing. So you come that the electron beam describes a circular path in the magnetic field, which can be explained as follows. So this path is circular. So whenever an electron enters a magnetic field, normally or in perpendicular directions, it will follow a circular path. So that means that this can be the radius of the circular path R, and this can be the center. So we are explaining why it follows a circular path. One shall come and see that, first of all, current flows in an opposite direction to that of the motion of electrons. Therefore, when you apply Fleming's left-hand rule, the force on the electron is downwards. I think we saw that in the illustration. And the electrons are deflected downwards, describing a circular path. Remember, for circular path to occur, for circular motion to occur, there should be a centripetal force. So the necessary centripetal force for circular motion to occur is provided by the magnetic force. Therefore, that means that magnetic force is equal to centripetal force. Then we shall substitute for magnetic force, which is BEU. B is the magnetic flux density, E is the electronic charge, and U is the speed, is equal to mu squared R over R. M is the mass, speed, and the radius of the circular path. So where is that electronic charge? And is a constant, so this will always be given in the question. Then we have M, which is the mass of the electron, and it's given by this. If it is an electron, the mass of an electron is this, and it is a constant, so it will be given in the question. Then U is the velocity of the electron, as we saw in the illustration. R is the radius of the circular path. B is the magnetic flux density of the given magnetic field. So you have defined those symbols. So you come here and say that when the electrons move out of the field, the magnetic force becomes zero and electrons move along in a straight line, which is tangential to the circular path of the point of exit. That is why we saw here that after this point it is straight, it is linear, because there is no longer magnetic field. So with that formula, we shall also go through this question. Question 1 came from UNEB 2003 paper 1 question 8C, and it says a beam of positive ions is accelerated through a potential difference of 1 exponent 3 volt into a region of uniform magnetic field of flux density 0.2 Tesla. While in the magnetic field, it moves in a circle of radius 2.3 centimeters. Derive an expression for the charge to mass ratio of the ions and calculate its value. So we shall derive a formula which we shall use to get the charge to mass ratio, and also substitute to get the value of the charge to mass ratio. Remember, I told you charge to mass ratio is the same as specific charge. So when they say specific charge, just know that it's the ratio of charge to mass. So we shall start by saying that electrical work done is equal to kinetic energy gained by the ions. Remember here we are not given the speed of the ion, of the positive ion, meaning we have to first get the speed using this formula. So you come and say that Q VAK. Now we are using Q and not E, because if it was an electron we would have used E, but now it is just a positive ion. That's why we use Q. The equal to a half mv squared. That means that when I make V the subject, I'll come up with this. Now also know that because there is circular motion, when you see magnetic field, just know there is circular motion. So it means that magnetic force is equal to centripetal force. Therefore, you shall come here and substitute for the magnetic force equal to centripetal force. Then we shall cross multiply, take this on this side to give you this. Remember, one V cancels with this to remain with only V here. Then we remember that V is equal to the whole of this, so we shall substitute for V. Square both sides to come up with that. Our aim is to get Q over M. So we shall come and see that here, this M can cancel with the square to remain with only one M here. Then I have to make Q over M the subject. So take this M this side to come up with Q over M equal to 2VAK, which is here, and this one goes this here, this one also goes down. So that is the expression of the charge to mass ratio they wanted you to derive. Now we shall use it to get the value of the charge to mass ratio. First of all, we are given that VAK is this and flux density is that. Therefore, you shall come and substitute. Also, R is that. So convert to meters to give that. Now, when I substitute, you shall come up with this VAK is that, B is that, R is that. Then use a calculator and get the answer they wanted. Then question 2 came from UNEB 1995, paper 1, question 10b, and it says a particle of charge 3.2 x ⁻-19 coulomb is accelerated from rest through a PD of 10 to the power 4 volt. It enters into a region of uniform magnetic field of flux density 0.5 Tesla. The particle describes a circular path of radius 8.94 centimeters. Find Roman 1 the kinetic energy of the particle on entering the magnetic field, and Roman 2 the mass of the particle. So you shall come as that Q is this, then accelerating PD is that, then flux density is that, and the radius is here. So you convert to meters to give you this. Okay. Then from 1 they wanted the kinetic energy of the particle on entering the magnetic field. We know that kinetic energy is equal to electrical work done, so it will be equal to Q times VAK. Therefore, come and substitute for Q and for VAK to give you the kinetic energy they wanted. That was Roman 1. Roman 2, they want the mass of the particle. Here we shall say that at equilibrium, magnetic force is equal to centripetal force. So each time you see magnetic force, just know there is circular motion. So it is equal to centripetal force. Therefore, come and substitute. Magnetic force is B2V. Centripetal force is mv squared over r. Then rearrange to make V the subject, it will give you that. But kinetic energy is equal to a half mv squared. Therefore, come and substitute for V, which you got in the previous slide. And remember that this now here and this cancels, remain with only one M. Okay. So the good thing, we know kinetic energy, and we know B, flux density, we know Q, the charge, We know R, the radius, and M is the only unknown. So simplify when I use a calculator, the whole of this will give me this numerator. Then make M the subject, and that will be the answer they wanted. Then question 3 came from UNEB 2009 paper 1 question 8b, and it says an electron having energy of 4.5 exponent 2 electron volt moves at right angles to a uniform magnetic field of flux density 1.5 exponent negative 3 Tesla. Find Roman 1, the radius of the path followed by the electron, and Roman 2, the period of the motion. So your first interpret this electron volt means that PD times the electronic charge. That's how they convert to joules. Okay, then flux density is here. Therefore, with that interpretation, you shall go to Roman 1, where they want the radius of the path followed by the electron. First of all, kinetic energy is equal to half mu squared. Therefore, make the speed the subject. Make sure the subject to come up with this as the speed. Now, after getting the speed, you shall remember that magnetic force is equal to centripetal force. So you shall equate the two, then make R the subject. This is the radius they want. So substitute for M. M is a constant. U, we have got it. B was given electronic charge is a constant. So that gives you this as the radius. Then for Roman 2, they want the period of the motion. So period is equal to circumference over velocity. Circumference is 2 pi r, and velocity was this, which you had already got. So 2 pi, then radius, which is here, divided by the velocity to give you that as the period they wanted. So far we have looked at the speed of electrons and also the behavior of electrons in a magnetic field. So now we shall look at behavior of electrons in an electric field, or what we call deflection of an electron in an electric field. So you come as that the deflection capital D of the electron. So that deflection means displacement from the original direction. So the deflection of the electron on a screen, which is located at distance capital L from the center. Know this word, from the center. We shall illustrate that of that plates can be obtained using the fact that it continues in a straight line after leaving the field, just like it was after leaving the magnetic field. So the same applies here. When it leaves the electric field, it will continue in a straight line. The difference is that now, when in an electric field, it follows a parabolic path, and when in a magnetic field, it follows a circular path. So let's first illustrate. We shall put the plates which provide the field, and those plates are separated. So P and Q are the plates. The length of the plate is x. That means half of it will be half x, and the separation of the plates is d. So these are the collection to terminals of a PD supply. And this will be the screen. They say the screen is located at distance capital L from the center. That is why this capital L is from this midpoint or the plate up to the screen. Okay, so always remember that capital L is from the center. So before entering the field, it had a speed of u and it was moving horizontally. Now in the field, it will move in a parabolic path, as you can see it here, and outside the field, it will move in a straight line. So here the speed was u, here the speed is v outside the field. So we can split this velocity into two components, the horizontal part, which is vx, and the vertical part, which is vy. Velocity is a vector quantity, so you also need the direction. Therefore, we shall get an angle to the horizontal, and that angle will be theta. So that means that y will be the deflection at the end of the plates. You know the difference? Here, the deflection capital D is the deflection of the electron on the screen. But this y is the deflection at the end of the plate. So there are two kinds of deflection. They can ask for deflection at the end of the plate or deflection on the screen. So if it is deflection on the screen, it will be from here up to here. But if it is deflection at the end of the plate, it will be y. Okay, so we shall derive some of the formulas. So from the above diagram, so here we shall first define P and Q are the deflecting plates. We saw that. Use the speed of electron on entering the electric field. V is the velocity of the electron after passing through the field or the deflecting plates. Vx and Vy are the horizontal and vertical components of V. Theta is the direction of the electron after passing through the deflecting plates. So we let Vk be the accelerating PD or the anode to cathode voltage. Let also V be the PD between the plates P and Q, and E be the electric field intensity between the plates. So these symbols will be used to derive some of the formulas which you shall use in this part of the video. So first of all is the speed of the electron on entering the electric field, so that it doesn't differ from the one we have already seen. So we shall come and just write and say, as already seen, the speed of the electron on entering the electric field is given by U equal to 2 over m. So you already know this formula, that's why we shall not bother to derive it. So our interest will now, this one we have already looked at it and even looked at the questions, but our interest will now start on this. So the velocity of the electron on leaving the electric field. That, in other words, they want the value of V. So the velocity of the electron as it emerges out of the plates can be obtained as follows. So we shall derive the formula we shall use to get the velocity as it emerges out of the field. So first we shall say that electric field intensity E is given by V over D. Remember, electric field intensity is equal to PD over the separation of the plates. We shall call it equation 1. Okay. Then we shall go ahead and say that electric force is given by electric field intensity times the electronic charge. But from Newton's law, that force is equal to ma. Meaning that when I concentrate on these ones and I make A the subject, I'll come up with electric field intensity times the electronic charge divided by mass. Okay, so now we have got acceleration. But remember, they want velocity. So we shall come and say that therefore, acceleration of the electron is equal to electric field intensity times the specific charge. Remember, this one is ratio of charge to mass, so it is called specific charge. And this is the electric field intensity. Okay, so I can rearrange to come up with that. I've got acceleration, then I remember that electric field intensity is V over D. Therefore, where there is E, I'll put there V over D to come up with equation 2 for acceleration. Okay. Then the time taken by the electron to pass through the plates is given by the distance or the length of the plate divided by the speed. Remember, time is distance over speed. Okay, so we shall call it equation 3. So now we shall go to the vertical component of the velocity. So the vertical component, we shall use the first equation of motion. Now Vy means vertical component of final velocity, Uy means vertical component of initial velocity, acceleration, time. So that is the first equation of motion. Therefore, we shall come and say that remember initially the electron was entirely horizontal on entering the plates, meaning the vertical component is 0. So Uy is 0. And we have already got the expression for acceleration, and it was this. Electric field intensity times the specific charge. Then you also got the expression for time. I think that was equation 3. And it was distance over, or the length of the plates over the speed. Okay, so what you're going to do, actually this expression is very vital, that vertical component of velocity is electric field intensity multiplied by the specific charge multiplied by the time taken. And we shall use it more frequently. So that is Vy, and that is the vertical component. What about the horizontal component? Now for the horizontal component, we shall just say that Vx is equal to U. So horizontally, the horizontal component is always constant. Why? Because it is not affected by the force. That is why it is U. Vx will always be equal to the initial velocity. So remember, initially it was entirely horizontal. That is why we are saying Vx at any time t is equal to initial horizontal velocity. So now that we have the fine horizontal and vertical components, we can get the resultant of the two components to come up with the velocity they wanted. And also remember, it needs direction. So remember, horizontal component was in that direction, vertical was in this direction, meaning the resultant will be from start to end. This will be the resultant velocity v, and also the direction is needed, theta. Remember, it's a right angle triangle, so it will say this is v, y, and this is v, x. Okay. That means that tan theta will be equal to Vy over Vx, as you can see it here. And V will be equal to Vx squared plus Vy squared, everything under square root. So those are the formulas. That is the formula I shall be using to get the velocity after leaving the electric field. But for the case of calculations, we shall first derive all the calculations which are necessary, then we shall go to the questions. So another part 2 will be deflection at the end of the plates. I think you saw the Y on the diagram. So how do we get that deflection? So the deflection Y of the electron as it emerges out of the plates can be obtained as follows. So we shall draw our right angle triangle, then also draw a triangle for the distances. This is a triangle for the velocities, triangle for the distances. They are similar triangles. Therefore, for similar triangles, we shall say that Vy over Vx is equal to y over a half x. But my aim is to make y the subject. So I'll come and substitute for Vy. We already know Vy. That's the electric field intensity times the specific charge times the time taken. over Vx, which is U, equal to that. So when I cross multiply, take the whole of this side and this one this side, you come up with this line. Then make y the subject to come up with that expression, that a half times electric field intensity times specific charge times the time squared. So in other words, we are using y equal to a half a.t, because this is a and this is t squared, half a.t squared. Okay. What about deflection of the electron on the screen? So the deflection d of the electron on the screen can be obtained as follows. So we shall draw similar triangles, one for the velocity, another one for the distances. So remember, capital L was the distance from the center of the plates to the screen, and D was the deflection. Therefore, so we shall do the same for similar triangles, get the ratio, equate them, substitute for Vx and Vy, then cross multiply and make D the subject. And that will be the deflection on the screen. So there are two deflections. One was deflection at the end of the screen, at the end of the plates, and two is deflection on the screen. And we also have what we call crossed electric and magnetic field. So we have been dealing with them independently. We have first dealt with magnetic field alone, then electric field alone. But what if they are crossed together? So you are coming and say that if a magnetic flux density B is applied perpendicularly to the electric field, so that the electron passes undeflected through the fields, it implies that the magnetic force experienced by the electron is equal to the electric force. So each time you hear the word crossed electric and magnetic field, it implies that, and they tell you that the electron passes undeflected, it implies that the magnetic force is equal to the electric force. So that is the condition for crossed magnetic field and no deflection. Therefore, in presence of both crossed electric and magnetic field, it means that magnetic force is equal to electric force. Come and substitute magnetic force. It's an electron, that's why you use BeU, and electric force, electric intensity times the electronic charge. Then make U the subject, U will be equal to E over B. That was in presence of both. What about in presence of only electric field? So in presence of only electric field, that is when a deflection D will appear. And we have already derived this deflection, so we shall just come and quote. So when there's only electric field, we have this deflection. When there is a crossed electric and magnetic field, there is no deflection, and the speed is this. So of the formulas we have derived the formula for the velocity after leaving the electric field, and also the formula for the deflection at the end of the plates, and also a formula for the deflection on the screen, and lastly a formula for crossed electric and magnetic field. So those are 4 parts, and those will make that makes a list of 4 questions. So each part will have a question on its own. So the question 1 will deal with the first derivation which we got, and that was the velocity after leaving the plates. So this question came from UNEB 2012 paper 1 question 8b, and it says a beam of electrons is accelerated through a potential difference of 500 volt. The beam enters midway between two similar parallel plates of length 10 centimeters and are 3 centimeters apart. If the potential difference across the plates is 600 volt, find the velocity of the electron as it leaves the region between the plates. So that was the first derivation we got, the velocity after leaving the plates, or as it emerges out of the plates. So we shall first interpret the question. This 500, remember there are two PDs, but this PD is called, here the word, you can see the word accelerated, meaning this is accelerating PD. That is why you write it as VAK. Okay, then X, remember X in our diagram denoted the length of the plates. So if you read through this question, they said length 10 centimeters. That is why you put X to be 10 centimeters, which is 0.1 in terms of meters. Then D was the separation of the plates, and you see this word 3 centimeters apart, meaning this will be the separation of the parallel plates. So these 3 centimeters will be small d. Now you should remember that the symbols are very vital. All the letters we used, you are encouraged to maintain them. So for example, if D we use it for separation, don't again use it for something else. Okay, then V we used it to denote the PD between the plates. So here they said if the potential difference across the plates is 600, that is why we are saying this 600 is V. After interpreting, it is easier. Now next is to remember to quote the formula and then you substitute. So we already said that horizontal component is equal to the initial velocity, therefore Vx is equal to U, and that U is the speed of the electron initially. And we already saw this formula, 2 times electronic charge, which is a constant, times accelerating PD, divided by mass of the electron, which is also a constant. So that gives you the horizontal component of the velocity. But we also need vertical component. So vertical component, we shall first quote the formula that is equal to the electric field intensity times specific charge times the time taken. So this is PD between the plates, electronic charge constant, X which is given in the question, separation of the plates, mass of the electron, and the speed which you have calculated. So that gives you the vertical component of the velocity. So now that we have the vertical and the horizontal, we can be able to get the resultant. Remember the question wants velocity, meaning it wants magnitude and direction. So horizontal velocity component is that, and vertical component is that. Then the resultant will be this, and the direction will be that. So by Pythagoras, we can get the magnitude, which will be that. And then we use trigonometry. We can use tan, so this will be alpha, not theta. Theta was already used in the diagram. So change this to be alpha. So alpha is equal to opposite over adjacent to give you 63.43. Therefore, shall conclude by saying that the velocity is this in the direction making an angle of this above the horizontal. And that's what they wanted. So I believe you have grasped the first derivation. Now shall go to the second derivation. The second derivation was about the deflection at the end of the plates. So question 2 is about that. And it came from UNEB 2002, paper 1, question 9a, Roman 2. And it says, an electron gun operating at 3 exponent 3 volt is used to project electrons into the space between two oppositely charged parallel plates of length 10 centimeters and separation 5 centimeters. Calculate the deflection of the electrons as they emerge from the region between the charged plates when the PD is 1 exponent 3 volt. So first is to interpret what is given. So if you look at this electron gun operating, so this will be the accelerating PD. Then here they talked about length, so length is x. Then they talked about separation, separation is small d. Then they talked about the PD between the plates, and that is V. So you should make sure that you use the symbols correctly. Don't interchange the meaning. First we shall get the initial speed, that is square root of 2 times E times accelerating PD divided by mass, everything under square root to give you that velocity. Then from there we shall quote the formula for y. Y is equal to a half a, this is acceleration, and this is t squared. So acceleration is electric field intensity times the specific charge, and time is distance over speed. Then we shall substitute this a half, the 2 is there, V is this, E is that, X is that, but it is squared. Then separation is that, mass is that, and U is that, but it is squared also. Therefore, using a calculator gives you the displacement they wanted, or the deflection they wanted. Okay, then when we finished deflection at the end of the plates, we looked at deflection on the screen. So that is what this question is about. And it came from UNEB 1994, paper 1, question 8D, and it says, an electron of energy 10 kilo electron volt enters midway between 2 horizontal plates, each of length 5 centimeters and separated by a distance of 2 centimeters. A potential difference of 20 volt is applied across the plates. A fluorescent screen is placed 20 centimeters beyond the plates. Calculate the vertical deflection of the electron on the screen. Okay, so first we shall have to interpret what was given. So X was given as 5, D was given as 2, so you change to meters, and PD between the plates was given as 20, so which is that. What about capital L? Remember capital L, if you look at this diagram, the one we drew, capital L was the distance from the center of the plates up to here. Okay, so to get it, we are saying 20 plus 5 over 2. Now, why do we say that? Let's first go back in the question. Here, when they talked about 20, the fluorescent screen is placed 20 centimeters beyond the plates. I think we see that word, beyond the plates. That means that the 20, if you go to this diagram, starts from the end of the plates here up to the screen. Okay, that is 20. But there is also this distance, which is a half x, and our x was given as 5, meaning a half x will be 5 over 2. So that explains why we are saying 20 plus 5 over 2 to get the value of capital L. Then at the end we convert to meters. Okay, then kinetic energy was given in kilo electron volt. You have to convert it to joules by multiplying by electronic charge. So this 10 times 10 to the power 3 is converting from kilo electron volt to electron volt. Then to convert from electron volt to joules, you multiply by the electron charge to give you this as the kinetic energy in joules. But we know that kinetic energy is equal to half mu squared. Therefore, when I substitute, I'll be able to get the value of U. And U will be equal to this. Okay, now that I've got the value of U, I can get the deflection they want. Deflection D, capital D, is equal to electric field intensity times specific charge times the time taken times the L over U. Remember, time taken is X over U, meaning 1 U remains and it goes with this L over U. Okay, so substitute V, E, X, capital L, small d, M, and U squared. And that gives you the deflection they wanted. Then next, after that, we looked at what we called crossed magnetic and electric fields. So this question will be on that part, and it came from UNEB 1999, paper 1, question 10b, and it says a beam of cathode rays is directed midway between two parallel plates of length 4 cm and separation 10 cm. The beam is deflected through 10 cm on a fluorescent screen, placed 20 cm beyond the nearest edge of the plates, when a potential difference of this is applied across the plates. So this deflection is when there is only electric field. Okay. Then they said if this deflection is annulled, annulled means there is now no deflection, annulled by a magnetic field of flux density this Tesla, applied normal means perpendicular to the electric field between the plates, find the charge to mass ratio of the cathode rays. So first we will interpret the question. X, which is the length of the plates. If you look at the question, the length was that. Then D, which is the separation of the plates. Small d. Then capital D was the deflection. Here they said deflected through this on the screen. So that is capital D. Okay. Then PD between the plates, that is V. Then magnetic flux density, it's that. Now capital L will be, now in meters it was this 20, in meters it becomes 0.2. Then this is this one, half of this gives this part. So when I add the two, I come up with this, that is capital L. So after interpreting the question, you can now go ahead and say, for no deflection, magnetic field is equal to electric field. That means that electric field is V over D. Therefore, U will be equal to, make sure the subject will give you V over BD. Substitute for V, substitute for B, substitute for small d to give you this as the initial speed. Now, in the presence of electric field only, there was a deflection, and we know the formula for deflection, so shall quote it. Then we substitute for capital D, V over D. This is what they want, charge to mass ratio. Substitute for this, substitute for that. Then simplify. So when I simplify this times this, gives me that. But my aim is to make the whole of this the subject. So make it the subject, you come up with this as the charge to mass ratio which they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on Millikan's oil drop experiment. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, such that you can all benefit as a family.